Hello dear learners, welcome back for today's new session. As we know that we are dealing with a displacement method, that is a slope deflection method. Today we are going to take one problem on the same. So let us have a look at this problem. We are having a continuous beam which is fixed at A and C, and one more intermediate support is been given at point B. The spans are been mentioned here, and the EI for this problem is again to be taken as a constant. Now we know whenever we are going to come across this particular sort of a problem, we know the first job is to find out the friction moment. So as I said earlier, whenever it comes to a continuous beam, we have to separate the spans. So here I have separated the spans and I have shown the friction moment. Being the standard cases, we know the values of the friction moment. So MAB bar is equal to minus WL square by 12, minus because it is anti-clockwise about point A. Back substituting the value of the spans and the loads, we are getting MAB bar is equal to minus 125 kilonewton meter, and by putting the value we are getting MBA is equal to 125 kilonewton meter. Is it okay? So anti-clockwise, so minus, clockwise, so plus. Similarly, next spans consideration, it is a point load at certain distances from the supports. Is it okay? So here, being again a standard case, we know friction moment about B will be WAB square by L square, and putting the values of the point load and the spans here, we are getting minus 90 into 1 into 2 square by 3 square is equal to minus 40 kilonewton meter. Is it okay? Now for the second span MCB, back substituting the value, we got a friction moment is equal to plus 20 kilonewton meter. After that, the next job is to identify the boundary condition of this problem. So here we can see at end A and at end C both are fixed end, so the displacement at this point shall be equal to 0. Is it okay? So theta A and theta C are taken equal to 0. Similarly, nowhere in this problem it has been mentioned there will be sinking effect or the supports are placed at different level. So obviously the deflection at that point will be equal to 0 for both the spans AB as well as BC. Moving ahead, the third job is to be understanding the equilibrium condition. So in this total beam at point B, the B has to be in the equilibrium. So how it is to be in the equilibrium? Final end moment for span BA and BC about point B should be equal to 0. So MBA plus MBC should be equal to 0. So this is the important equilibrium condition which we have to understand for this particular problem. Now let us move ahead and see once again the same beam, and we will be applying the slope deflection governing equation. So we know this is what is a slope deflection governing equation about point A. So considering first span AB and applying the governing equation, MAB is equal to MAB bar plus rotation effect about A, far end effect about point A, and the deflection effect. So putting the boundary conditions in this equation, we are getting a simplified equation. MAB is equal to minus 125 plus 2EI theta B by 5. Is it okay? So here boundary condition theta A was equal to 0 as well as delta AB was also equal to 0. So after putting those values, we got a simplified equation number 1. Similarly, for the next span or the next friction moment MBA, back substituting the boundary conditions, we got a simplified equation number 2. MBA is equal to 125 plus 4EI by 5 into theta B. So we got for the first span two equations, 1 and equation number 2. Is it okay? Similarly, let us work out for the next span, that is BC. Already we have worked out the boundary conditions and that are been mentioned in this particular slide here. Let us move ahead, consider the second span BC and find the what we can say, final end moment due to the various effect, that is effect due to the applied load and the effect due to the rotation about point C. Is it okay? So here this is what is the governing equation, and putting the boundary condition theta C being fixed is equal to 0 and theta BC is equal to 0, as there is no any sinking effect given for this particular problem. So after simplifying that, we have got equation number 3. Similarly, for the another fixed end moment, that is MCB, again the governing equation, again the boundary condition, substitute it, and we are getting a simplified equation number 4. So overall right now we have 4 equation, 2 equation for first span AB and 2 equation for the another span BC. So all these 4 equations are to be taken further for the simplification or the analysis of this problem. So here we know after this we have to understand the equilibrium condition about joint B. So here we can see this particular free body diagram of span AB and BC. So here about point B, final end moment MBA should be MBA plus MBC should be equal to 0, and MBA and MBC, which are the final end moment about point B, are been already worked out in equation number 2 and 3. So these two equations, that is equation number 2 and equation number 3, are to be simply added and simplified further. So here after putting this equation number 2 and 3 in this equation, we have simplified and got a value of EI theta B equal to minus 39.8475. So calling this as equation number A. So in this problem also there is only one unknown or one displacement happening about point B because of the simple support, that is roller. Is it okay? So that displacement we have worked out by the set of simultaneous equation, and that value we have got EI theta B is equal to minus 39.84. Now once we get that single unknown or that single redundant value, now we know the rest of the things, that this value is to be substituted in all the earlier equation which we have already found out. So taking that value of EI theta B and substituting it in the equation number 1, we got MAB is equal to this much. Is it okay? So minus 140.93 1 kilonewton meter. Take equation number 2, put the value of EI theta B and get the value of MBA is equal to 93.125. Next, third equation, put the value of EI theta B and we got MBC is equal to minus 93.125 kilonewton meter. Similarly, MCB we have worked out, that is equal to minus 6.652 kilonewton meter. So these are the various moments happening due to the effects happening on this particular beam. One effect was due to the applied loads and second was due to the displacements occurring at the various points. So these are the various values of the moments, and these are nothing but these are the final moments. Now all these final moments are to be utilized for further analysis. So already we have found out the results, that is the fixed end moment at each and every point for each and every span, and according to or from that particular values we have constructed the final end moment diagram. Is it okay? So this is obviously what final end moment due to the problem. In this we have A and C as a fixed end. Is it okay? So after finishing with this, we know the next job is to find the free bending moment diagram. So we know the first span imposed with the UDL and its free bending moment is WL square by 8. Substitute the value and get the value of the 187.5 kilonewton meter. Is it okay? Similarly, for the another span we have worked out, and after finding out the fixed end moment, final fixed end moment diagram and free bending moment diagram, for finding out the resultant we have to superimpose these two diagrams. So this value here is going to give you the resultant moment acting on that span. Similarly, for the another span, this is the resultant value. So this is how we have to work out the values. Now one more thing to be very much specified at this moment, the problem actually is not been yet finished because still the unknowns are existing, that is reaction at A, reaction at B and reaction at C. All these various values are to be worked out from the basic knowledge of equilibrium condition and the basic knowledge of every span to be taken as a free body diagram, show all the moments there, show all the reactions, all the various loads acting on that, and applying the various boundary condition, or other to be very specific, while taking the free body diagram of individual span, for an example AB span, we can isolate it, we can show all the known and unknown forces and applying the equilibrium condition about one joint and getting that unknown present into that particular system. So this is how we have to work out the reactions, which is the last objective. Is it okay? So this is the methodology by means of which we can find out the final resultant bending moment acting on that beam and also the reactions happening at that particular point. So moving ahead, in the next lecture we shall be definitely looking after another numerical in which we shall be dealing with the three spans imposed with the UDL and the point load. Now as far as the knowledge of the reactions are concerned, how the reactions are to be found out, definitely all these methodology are been already applied into the earlier lectures when we were dealing with the fixed moment. After finding out the fixed moment, we used to find out the unknowns, that is the reactions happening into that particular by considering an individual span showing all the moments, all the loads, all the active and reactive forces and applying the equilibrium condition. Ultimately we used to get the remaining unknown into that particular problem. So this is what we have for today. Have a nice time. Be happy. Thank you very much.